Welcome to Unit 5, Lesson 21, Cylinders, Cones, and Spheres. We are almost done with this packet. Today we're going to be working with all three of those figures, and it should be a fairly quick lesson. So first part is there's an argument going on with our math squad, except this time Han has joined the party. They've all calculated the volume of a sphere with a radius of 9 centimeters, and they got 4 different answers. Han thinks that the volume is 108 cubic centimeters, and Jada thinks 108 times pi cubic centimeters. Tyler calculated 972 cubic centimeters, and May said it was 972 times pi cubic centimeters. Do you agree with any of them? The place that we need to start is the volume of a cylinder is 4/3 times pi times the radius to the third power. Off the top of my head, the very first thing I'm thinking about here is the radius is 9 centimeters, which means that we are going to take 9 to the third power, which is equal to 9 times 9 times 9. I know that 9 times 9 is 81. I know that 81 times 9 is going to be well over 700, so I'm immediately going to eliminate Han and Jada. They both made some kind of serious mistake. I doubt they used the correct formula for this. So that leaves me with Tyler and May. My next step is I'm going to decide if 933, or 9 to the third power, 9 to the third power, 81 times 9 is 729. So what I have right here, the volume is equal to 4/3 of 9 to the third power times pi. Okay, I'm not quite to my value of 972, but I am to this point where I can multiply this value, 729, 9 to the third power, 729, by 4/3. So I can multiply this times 4 and divide by 3, and I get 972. That's just the product of these two values right here. So clearly, Tyler forgot to multiply by pi. This value would be 972 cubic centimeters. May is the one that got it. Do you agree with any of them? I agree with May. Tyler must have forgotten that to multiply by pi or something like that, but I agree with May. May, explain your reasoning. My reasoning would be when substituting the value of 9 centimeters into the volume or into the radius for the volume of the cylinder, the calculation comes out correct. So that's, again, the whole thing with explanation is explaining that piece that we're going to be dealing with. So the volume of the sphere, the next part of it, talking about a sphere, volume of a sphere is given below, 288 times pi. So the statement below, giving us an equation or statement, says the total volume, 288 times pi, is equal to 4/3 of the radius cubed times pi. What is the value of r in the sphere? Explain how you know. So again, what we're going to be running into is we're going to have to show that I can verify that my radius that I find is correct. Understanding that we have the total volume, we have the ratio 4/3, we have the ratio of pi, the only unknown value is the radius, so we can solve for r. 288 times pi is equal to 4/3, and you'll notice I'm going to switch my orders around, commutative property here, because I want to get r out here by itself. It just looks a little cleaner to me. Divide the right side by 4/3 times pi, leaving us with just r to the third power. Divide the right side by 4/3 of pi. And you'll notice that we're into this part again where we can take pi divided by pi as 1. That's eliminated. And when we divide by a fraction is the same as multiplying by the reciprocal. So for me, I find it easier to take my value and multiply it by the reciprocal of 3/4 rather than do division of 4/3. It is the same outcome. It won't matter what we have there. But the hard part is when we want to go to a decimal, a lot of times we think, oh, 288 divided by 4/3 is just 1 1/3, so I can divide by 1.3. You can see that it comes out to a really long decimal. So it is really critical that we recognize this step of multiplying by the reciprocal. And that reciprocal of 3/4. Whoops. Try that again. 288 times 3. So multiply by the numerator, then divide by the denominator, 216. You might also be saying, well, why can't I just do the decimal of 3/4 as 75 hundredths? And that would be fine too, because this is a terminating decimal that you can actually predict right off the top of your head and get exactly right. So 216, we find out now that the radius to the third power is equal to 216. What that means is that I have one factor here, r, that's been multiplied by itself, one single number multiplied by itself 3 times to get 216. To be able to calculate that value, unfortunately, this calculator doesn't have all of those pieces, I don't think. No. And then we have trigonometry ratios. It's not in there. Yeah, see, these pieces aren't going to really help us. What we're looking for is a button that's kind of like this one, the square root of a button, except the square root is only with 2 values. So when we're looking at this, if we see something that's to the third power, we need to have a different root ratio that has a root index right here that matches. So we're going to take, since this can be called r to the third power, r cubed, we are going to take the cubic root of r cubed. So on this side, we'll take the cube root here on the right to just get r by itself, 216. We take the cube root of 216. This value is on cell phones if you have that capability at home. It is also available on most other scientific calculators, but you're looking for this button right here. It has 3 as a root index right here. So we type in 216, and then we simply touch that root, that cube root index, and we get 6. And what that means is that if we have the right radius now, it should come out to 288 times pi. So let's start with that piece. Let's take 6 on our other calculator. 6 times 6 times 6, 6 to the third power. Whoops, let's change this back to radians here. Uh-oh, I don't know what I did to my calculator. I messed it up. Oh, there it is. Okay. So I just took it out of a function notation that we're going to be talking about. It's called scientific notation. We're not going to mess with that yet. But 6 to the third power, 216. And then I want to multiply that by 4/3. And it's like I'm clearly messing this all up. So I don't know what I did to it. So 216 times 3. Well, that's not fun. 6 to the third power times 4/3 is 288. So I know that I have the right answer. Radius is equal to 6, and or 6 units. And I know that's true because when I substitute it back into my formula for r, this expression becomes equal to this expression. Okay, sorry, that took a long time. I told you this was going to be a shorter video. So we're going to skip that next part, 2.3. We'll come right here to the right fit. We have a cylinder with a diameter of 3 centimeters and a height of 8 centimeters. It's filled up with water. We're supposed to figure out which of these 4 figures down here below have the same volume. I could make some predictions based on some things that I've known with scaling, but I'm not going to today because I just want to verify these pieces are here. First thing that I'm going to recognize is what the actual volume is up here. To do that, I need to know the radius of this cylinder, which is going to be 1.5 centimeters. So my total volume for this cylinder is pi times the radius squared times the height. So the volume is equal to the radius of 1 5/10 squared times the height of 8 times pi. I'm going to leave these in terms of pi, all of them, so that I should see an exact value for each one that would be the same. So this 1 5/10 is 2 25/100 when it's squared times 8 times pi, will give us a total volume of 18 times pi cubic centimeters. So that's our target. We want anything that equals 18 times pi cubic centimeters. So this next one, a cone with a height of 8 centimeters and a radius of 3 centimeters. Now we might be fooled into thinking, oh, okay, the radius and the height are exactly the same. So the cone would be 1/3 the volume of the cylinder. Okay, then it won't be right. But here's the thing, this is a diameter. So the cylinder is larger, the height is the same, but the cylinder with the base is larger. So let's go ahead and calculate 1/3 of the area of the cylinder, or excuse me, the area of the base will be the radius of 3 squared times the height of 8 times pi. So again, the same type of thing that we've been working with. The volume of a cone, 1/3 pi r squared times h. 3 to the second power is 9. 9 times 8 is 72. So I have a volume of 1/3 of 72 times pi. And I'm going to jump back over to my calculator. I'm going to keep using this one though, because for whatever reason the other one's messed up. 72 divided by 3 is 24. My volume is not equal. And then explaining my reasoning, well, when substituting the height and the radius into the formula, I find out that it's not equal. The cylinder, here's a different cylinder that's equal to the radius. So we see a diameter of 6 centimeters, so the radius will be 3 squared times the height of 2. This one actually looks like it'll probably work because we're now looking at a volume of 9 times 2, which is 18 times pi. This one is equal because it has the exact same volume, 18 times pi. Rectangular prism, remember the volume is equal to length times width times height. So we have 3 times 4 times 8. And I can tell right away this one is not going to be the same volume because this is equal to 12 times 8. So a total volume of 72 cubic centimeters. And now you might be thinking about, well, what if you take 18 times pi? Let's go ahead and do that. We'll do the approximation of 18 times pi, but I don't think that that's going to be a value that we really need to worry about, or a value that's going to come close to 72. Yeah, see, our volume up here is approximated at 56 and 5200 centimeters to the third power. So the rectangular prism, not equal. Again, substitution into the formula does not yield the same result. Let's talk about a sphere. A sphere, the volume is equal to 4/3 times pi times the radius to the third power. This sphere has a radius of 2 centimeters. So we're looking at a total volume of 4/3 times a radius to the third power, 2 to the third power times pi. That's going to be 4/3 of 8 times pi. I have 4 times 8, numerator times the whole number, so that's 32/3. And right now I know for sure that this one's not also going to work because 3 times 18 is not 32, so this one is not equal either. Okay, and the way that we figured it all out is just by calculating the volumes of all of them, substituting the known values back into the formulas that we're given. Whenever we need to explain reasoning about why something does or doesn't make something true, all we're doing is we're comparing by using substitution to compare one value to another value. And if it doesn't come out to that equal value or making the equation true, then we know that it's completely false. It just won't work. Okay. So you're welcome to give the next one part or next part a try. I told you the video is going to be short, so I'm going to skip it. But Thirsty Crow wants to raise the level of water in a cylinder or cylindrical container so it can reach the water with its beak. So maybe that crow is just really, really smart. From this lesson and from this unit, this last half of the unit, you really need to know a few things. We need to know how to find the volume of all of the figures. We also need to know that from that volume, if we are given everything but one of those factors, we should be able to find it. So if we know the total volume, we can find the radius from any sphere. That's what we learned in this one. We also learned how to compare a lot of different objects, from water bottles to buildings, or buildings to balloons, all these similar shapes that come into play, or maybe not even similar shapes, that their volumes can be equal, but the formulas are really the key things that we have to have from this, to be able to understand the volume perspective. We need to understand that cylinders have a volume of the base, pi times the radius squared times the height. A cylindrical base, or a circular base, times the height. Cones are just simply 1/3 the volume of a cylinder with an equal radius and an equal height. Spheres have a volume of 4/3 times pi times the radius to the third power. And then rectangular prisms are just simply that volume of length times width times height. So I'm really proud of you. You've been working really hard on this lesson, I can tell, or on these lessons. You've come a long way from the beginning of these lessons on volume. Didn't do so well, and now we're out here at the end, and I'm seeing really good scores. You're doing a really good job. I'm really proud of you. So we will have one more activity before we take the end of unit test. Thank you for your dedication. Please let me know how I can help you out with this. And sorry the video is longer than I had thought it would be. Take care.